Okay, let's get started. So let's talk about profiling Linux stuff for performance and troubleshooting reasons. Not only Linux, but also how the applications and databases interact with it and how that, right? So of intro, I've been in database performance for for over 2 years, mostly Oracle. Authored a book that got translated language. I've worked with other engines, but I don't really expert in the internal of Postgres or MySQL, but a database should into OS and I use them and so on, so that everything play along nicely. So that's what I will talk about today, right? Since my journey into independent SQL engines, I co-founded called Gluent. I was the CEO there as well, but didn't want to turn into full-blown. Then now I'm more a technical guy doing tech advisory at Gluent of patents and so on. And now I'm also a secret project, and what I'm doing is actually a small part secret project. Okay, so I'll show you an intro into the Linux task state sampling method. Then we do a bunch of demos, and I'll also show you how to have this always on, so that when a problem happens in the middle of the night and you will troubleshoot it next morning, you can still go back in time and do a pretty detailed drill down into understanding what the heck happened, right? And in the end, I'll have some links to my other videos of this stuff as well. So because we don't have much time, well, just I'll show you what's possible, right? And I'm not gonna blab too much about it. Okay. So, and by the way, why do I prefer low-tech tools or this kind of tools like you'll see, as opposed to eBPF tracing or like ftrace or dtrace in Linux, whatever? Then when you do a lot of troubleshooting at different customers, like I do nowadays, then you don't really have time to engineer a solution in their system, right? The problem is already happening. You cannot, you don't have time to upgrade the kernel, and you don't have the permission to upgrade anything anyway, right? So you just have to, when a problem happens, they will call you. You have to be able to start looking into it right away, and usually without installing any heavy software packages and so on, right? And sometimes you don't even have root access, right? And the solution or the idea is, okay, let's just use the existing instrumentation that's already enabled in Linux anyway, right? Let's use it in perhaps in a more comprehensive way or in new ways, right? And this instrumentation is always enabled anyway, so we will just consume or read it from this file. Okay. Okay, so I still follow a top-down approach, and I drill down into where the problem is and where the higher level symptoms point me. Sometimes they point me in different directions. Sometimes it's a memory problem, whatever. Sometimes it's not an OS problem at all, or often, sometimes it's an application problem. Or it's a problem in the database where an execution plan has changed because somebody dropped an index or optimizer statistics problem, right? And suddenly you're doing 10 times more I/O for the same amount of work, right? So this is not something you go and solve at storage level. This is something you solve at application or SQL execution plan level. Do less I/O, then it's going to be faster, right? So I still, I follow this top-down systematic approach, but today's talk is not about that. Today's talk is about the OS and your database or application touch point only, right? So if your systematic troubleshooting points towards here somewhere, then I will show you useful tools. Okay, so the traditional approach, or very, very old school sysadmin approach is that whenever there is a problem, then log into the server and check the utilization of something, right? And when the utilization is low, then you say, hey, therefore you don't have a problem, right? Well, that you cannot really do it like that, right? So, 30 years ago, you didn't have better tools than just the utilization tools. But nowadays, in 2020, you do have quite a lot of tools, and many of them are built into proc file system. Okay. So what I propose, or what I have used for years now myself, is thread state analysis or task state analysis. So essentially, first of all, you have to realize that any application, any database engine out there, it's just a bunch of processes, or a bunch of threads inside of a process, but it's the same thing, you know, at high level, right? And now these threads or processes, they will do stuff. Let's say the green color is that they run on CPU, the blue color is that they maybe issue a synchronous I/O and go to sleep. The OS puts them to sleep, or they voluntarily go to sleep because they cannot get some sort of a lock inside the application, and they voluntarily go to sleep until the application wakes us up because the lock is released, right? So essentially, we will just sample, you know, every second, for example, we'll sample what all these threads are doing. You know, this is not tracing. We're not going to slow anything down. We are not going to attach to somewhere with strace or whatever, potentially crash the program and so on. So we are just sampling the already existing proc file system, right? And this will give us an idea of roughly what these application threads were doing, you know, at different points of time, right? And for database engines, because databases tend to do so much I/O, right? Well, many of them, not all, like this guy, I mean, then, you know, this approach is pretty cool because we can measure which system call we were in, where in the kernel we were waiting, and so on, right? So this is the approach what I'm proposing. Let's start sampling what threads are doing as opposed to measuring the utilization or something like that here, right? We may still have to go to this level, like IO stat, if we see that everybody is waiting for IO a lot and so on, but let's look into this approach first. Okay, again, I'm not saying that these tools, this sampling will replace everything else. Absolutely not. These other tools will be still very useful and, you know, used every day. So proc file system sampling will sort of, or threads state sampling complements other tools, right? But other tools are still going to be needed, including your database optimizer analysis tools and then so on, right? Okay, so actually, when you run PS, you know, the most standard tool of them all, or PS also reads the proc files, right? So I'm actually going to start the demo from using PS, right? So when you run PS, you gotta use PS minus capital L, because otherwise you don't see all the threads, right? Otherwise you only see the process ID or the thread group leader, right? So that's the number one thing. I mean, very, very relevant for MySQL, for example. Okay, and you know, now we can choose your own columns to show. So here is one. Well, one of the columns is the thread state, right? And where it comes from is when you run PS and you want to show the thread state, or top shows the thread state as well, it samples it, but it doesn't really summarize it. Then this comes from process ID status. And if I go back to the previous slide, if you have a multi-threaded process, you have process ID, task subdirectory, and every single thread under your process is listed here as well as like a pseudo directory, right? And on that you have this the stat and status columns, and this is where these tools like PS and top will get their info. You know, they will get it from here, and that tool also reads it from here. Okay, and I have these different task states. R means you are either running on CPU or you're trying to get on CPU. You're in the CPU run queue. D usually means not always, as I will show you. Sometimes when you're stuck in the OS kernel level before even getting to the IO submission part, then that will show up as D as well. And S is basically, you know, typically when you voluntarily go to sleep, you know, nano sleep and stuff like that, or it's waiting for some software and so on. So that's the high level overview. And you know, when you run PS and show the state, you see, you can just say, okay, show me all processes in the system, but only show the state and the process, you know, command name, right? And then I don't want to see all these thousands of lines on my screen. I want to summarize it, okay? So sort unique minus C essentially does like group by, like a group by in SQL. You see, we have 27 processes in this case who happen to be in sleep state by this you know, program SSH schema, right? And this of course does like a, you know, this is like an order by the, you know, show me the biggest number of processes first, and this is like limit 10. It's like SQL. It's like very poor man's SQL. Unix sysadmin SQL, essentially. Okay, and here I've done the same, something similar with capital L. That's what you should do as well. It's like, hey, let's show all threads, because you can have many threads active at the same time, and show the program name, and also show me the wait channel. The wait channel is the Linux kernel function name where you're stuck. So if we are sleeping in this function. This is the function which called the OS scheduler function and put itself to sleep, right? By the way, you gotta run this with sudo on or as root if you want this column on modern Linux versions, like version 4 and onwards, and so on. Because the newer versions, they hide this info from you. Didn't want to show you everything. Didn't want to show you kernel memory addresses accidentally and so on. So, but when you run it as root, you will see a more full picture. Okay, so I'll come back to that. And here is like, hey, let's add a filter. Let's add a where clause to our sysadmin SQL, right? And let's only filter the R and T. Only the states in R and T. So these two states are on Linux, which contribute to Linux system load, right? Unlike classic Unix or other Unixes, Linux includes the D state into system load as well. And you see, I actually have 32 CPUs in this machine, but I already have 64 Java threads who are trying to be on CPU. More and more threads who are trying to be on CPU. So this will show me an idea of how much demand we have for usage, right? So the amount of threads in the R state in VMstat would also would show that. So in case this is a different target. I just killed the previous command, ran a stress test with threads or processes in this case, and that's the number. But if I have more processes who try to get into CPU, you see the number bigger than the number of I have, right? More processes competing CPU than CPUs, right? That's why the CPU chain is at 100%, and that's why. Well, yeah, that's it. You see, I'm using clause here again. So this is what you can do with PS, not even having any extra tools, right? So I'll explain some reasons which take processes into these different states. So sometimes when you do blocking I/O, well, not sometimes, when you do blocking I/O, you wait, and the operating system puts you to sleep, you'll be in the D state. Also, when you're not trying to do the I/O, but there's a memory shortage and your memory has been paged out, and you have a hard page fault, then you're not going to be in an I/O call or anything, but you're still going to be sleeping and waiting in the D mode because the OS is doing I/O for you, essentially, right? But things like now sleep or like semaphore operations, these will show up like sleep. Futex and even like when you want to read from pipe and so on, these are like interruptible system calls, and they show up as S. And one noteworthy thing is I/O get events. So MySQL is also doing asynchronous I/O. Oracle certainly is doing async I/O, and the checking whether your IOs are complete, this I/O reaping, this shows up as sleeping. So this doesn't actually contribute to Linux system load, unlike other I/O. Okay, I mentioned that disk sleep is, by the way, not only for disk I/O waits. Here is proof if you want to read source code or Linux source code. Here's an example that we are trying to get a semaphore. Essentially, we are to get the lock on the inode, I think, and if that fails, we are going to go to sleep, and we are asleep in this disk sleep. So essentially, we are not actually waiting for I/O to complete and even got into the part of submitting the I/O. We are stuck in a file system layer, for example, and waiting for a lock, essentially, because of contention, and that will also show up as disk sleep. So D state usually is disk I/O, but not always. And by the way, you can look at my recent blog entry about Linux system load, where I explain how is it possible to have a system of 3000 while the CPU utilization is like under 100%. It's not even 50%. And when we drill down deeper, will see there are a lot of Linux kernel worker processes for some reason, and we'll look into the reasons. So let's do some demos, and as I said, I'm just gonna do a fairly quick and shallow walkthrough of what's possible, and happy to answer questions later. Let's let me run a couple of benchmarks, and so let's just dstat output. You can use top or whatever. Let me just clear this. You can use top or whatever, and you see it's doing well, it's doing 20,000 writes per second, 8,000 reads per second, and then plenty of CPU idle time. So it's like only the CPUs are only like 20% utilized or something. So I have plenty of idle CPU time, right? So I could say, hey, I'm just gonna run top. You see, but you're part of the picture. Top CPU utilization doesn't even sample that. Every time it refreshes, total CPU for that process summarizes it here. And by the way, this is where let's focus on MySQL. If I look into MySQL, you would only see one line here, right? But that's when you do capital H, when you would see all the right. So remember I talked about like PS and top to show you that they sample this. They don't sample the CPU. They will just of this every CPU counters for all. But this S threads kind of eyeball it. Like you see some most of these and a couple of also you can kind of see that hey, that is mostly waiting for this deal on C. So but the convenient way to do that you can totally do it if you want to, and or use the PS commands with sort and unique like I showed previously. Okay. Anyways, so to the demo. So we have a bunch of I have a tool called Linux Process Snapper. I'll explain the other tools in a moment as well. And basically it's an open source tool. It's just a Python script, so you don't really need to like install it as an RPM or like a heavy some sort of an agent. It's just a Python script, right? And it can even run on very old kernels, on Red Hat 5 and so on. And the basic usage doesn't even require root access, right? So I'll just run it so you'll see. So if you ever wonder what's going on in your system, why is the load like this, you just run, instead of PS, you run PSN. Linux Process Snapper. So this will take snapshots and sample of your thread and show you. You see, end of story. So it runs for 5 seconds. It samples, every thread it finds, and default it only shows you those states, the summary of those states of running on CPU and D, R and D. So if you want everything, so I could just say -A here as well. Let me just get there. Let me just zoom in to MySQL first, okay? So I'll just say, let's only look into MySQL. So that will show you this output. You see, now in the last 5 seconds, 11 threads were on waiting for D state on disk IO, and less than 1 thread. So that's like in summer, less than 100% of a single CPU were utilized, right, by MySQL run CPU. And as I mentioned, add -A to show all states. That's a sleeping state, and there are other, for kernel threads, you have other states as well. And you see, I have 39 threads that are sleeping in MySQL. And that's not necessarily a problem, because you may have a bunch of MySQL connections that are idle. They are sleeping, waiting for next message to arrive from some socket, or they are background threads which don't have any work to do right now. And you can drill down into this now by adding more columns into this group by operation, essentially. So let's just say, let's add the system call. You gotta run this particular column with sudo, because modern Linux versions, they sort of hide, they don't give you access to it they don't know kernel addresses and so on. And you see, like it for sleeping threads, doing nothing, not contributing to Linux load. They are waiting for a system call, right? And as I mentioned, you see, we have events. So these are now IO reaping, IO completion checks. Also, this is a special thing to remember if you use this technique. IO get events doesn't show up as a disk because it's it is an interrupted syllable call, you know, interrupted by sending it and so on. And you see a bunch of threads waiting for that. And if you now have, okay, question that which thread, add the ID or the thread ID here as well. So this will, you know, this as well. Well, PS doesn't show you the system, but you know, to the task. And you see, you could look into, you know, the task, the T of these threads, which are, you see, there are synchronous IO, right? And this thread ID, you can now link. You know, you go to performance schema dot search for, okay, show me all the threads where the IDs are, you know, whatever psnapper just showed you, right? And you see this IO threads, which are and apparently they do async, at least with my configuration. Okay, so I'll go back to mode. You learn that. So let's, you know, the one as well. That if you're doing, you know, we're stuck somewhere. So first, you're running on CPU. Little I can show here. This tool doesn't do profiling, perf for that, and but whenever you want to know where you're sleeping, right? For example, here we have an which some XFS log write, and whenever you see IOS, means that I managed to submit the IO, and now we're waiting IO schedule so that the over would sleep, so that, you know, that we could always complete it. But you see some weirder thing. For example, submit IO8. Submit means that fsync got sleep because it wasn't even able to it, you know, queues at OS for that particular you know, the queue for that already full. We couldn't even submit that, right? So I'm not gonna go troubleshooting right now and then like one. So that's, but and there is more. You see, there's a p write. Here's a p read. Currently, you know, we had like, you know, all of sessions out of this threads of whatever I have who are waiting. So they're not even get to the submitting the IO. They are in a semaphore somewhere. Okay, and now you have the question. Okay, what's in the kernel lock? Is it? We're stuck. You know, so this is right. So this go have separate videos. I will try to not spend. We can sample back as well. And again, we are not using BPF3, which has to read pseudo file system. Okay, so this output is very wide. You might want to, you know, send it to a text file or something like that, or use a terminal line which can scroll. And let's look into the top reason. Let's highlight. So there is, if I add this together, then one thread. There is like a threads, I guess, which are for a semaphore in Linux of actually doing IO. Now when you scroll right, let's see what happened, right? So file update time. I mean, the stack trace tells you what led you here. The wchan column is essentially a column. This is where we called the schedule to sleep. These functions before this is the pattern that led us. And for some reason we wanted the file latest change timestamp, right? And for that you take a lock inode file in Linux kernel. But if you have a local, then others same thing. You see file update date time, right? So there is date time, you know, the sys time. So the last file mod time, but this is the last sys time. So basically, so this is where why you have f instead of fsync, for example. You don't wanna, if you have many threads who write into a file system file, they will want to modify the last modification date. This is the last read, and this modification is acted by a lock in the code, right? When enough processes do it or threads do it, then you get the contention. I'll stop here. There is so much more to say about it, but in the interest of, you know, covering everything I want, I'll just you know, leave it there for now. You know, but the top one here is, you see, we are using fsync. Okay, you know, we know, you know, depending on configuration, MySQL is fsync, or, you know, DB here, and we're not actually doing IO. This guy is not submitting IO. It's not submitting IO. It's not waiting for IOs to complete. It's waiting for XFS journal entries to be written to this by a kernel thread, and we have multiple, like over 4 threads waiting for that instead of actually doing work. If I add it together, it's like you know, 5 threads in total out of 16 threads or whatever I got, right? And you go all the way right. So see, the system call for this guy is fsync, like we see from here. Here we have a case of where f data sync, you know, that sync only the data but not the, you know, metadata stuff. even that waits. But I'll just take the top one, right? Because that's, you know, probably the most interesting. So, and yeah, okay. So this is not too useful to us. You know, basically the reason here is that you know, we are essentially, our threads, our MySQL threads, which enter the kernel here, they are not the ones who are responsible for syncing this to disk. There are kernel worker threads who actually do this IO or log XFS log flushing to disk in asynchronously and concurrently, right? And our threads just wait until the kernel worker thread will notify us, right? So I could either add kwork here as well to see those threads as well, but linking them together with this sampling, that's not a trivial, because kworkers are independent. So I'm gonna sort of just briefly show there is that there are some kernel activity threads here as well, but I'm not gonna go deeper into that, just again for brevity. So, and the question is, okay, so what can we do here in this particular case? Let me kill this benchmark. So you see it did about what is it, 100 transactions per second, and I'm gonna do something just for the sake of this demo. Just for the sake of this demo. So I was already, well, I guess I had in my tests I had even commented out 2 parameters. So this is like I switched them on and off a lot. So actually, let me take a little detour here, just because that's interesting. You see, I have enabled both parameters, fsync and odirect. Is odirect used or not? You know, so I could probably look into MySQL log files or something like that as well, but since this is a Linux session, then let's just do. Okay, so this is my MySQL DP. Let's do sudo lsof plus fg. This. So plus fg will actually extract and tell us some extra information. It prints out some flags. You know, let's see. Dir is here, so you see direct. So the fact that you see dir here, that means that direct was used, despite my kind of incorrect settings here, right? But what I wanted to show you is, or demo, is this. I'm gonna comment these guys out, and I'm gonna just say this. I guess MySQL ignored the first one, or just, you know, used the last parameter that I had uncommented. So I'm gonna set this parameter to flush method to direct no fsync. But before I do anything, I'm just saying that, hey, I'm showing this to you as a demo for performance, for showing a performance difference, right? It's just worth saying that there are some gotchas with this. You know, if you go to InnoDB documentation and you see before this version, and you know, some file system. So basically, odirect fsync was not recommended because, you know, it didn't work correctly. So, and even when you have a later version, then don't just go and enable these things without really, you know, talking to your vendor or some MySQL expert. Or if you are the MySQL expert, then, well, talk to yourself and reason about whether in the latest versions it is a safe thing to do. And, you know, but in some versions it was enabled by default, right? Or maybe it still is. So again, I'm not a big expert in that part. So, but anyway, so it exists for a reason. So let's. I just want to show you how the dynamics change. So, odirect no fsync. This means that we will not call fsync, which means that we are not gonna generate, or we are not gonna force and generate so much of XFS you know, journal metadata to disk either, right? And there is another thing, that odirect, you know, only will bypass the OS file system cache, so it will not, you know, end up in this buffered in the file system cache. But odirect does not force that the underlying disk actually flushes this thing from its cache to the persistent storage, right? So, you know, if you're on this EMC storage array or some enterprise storage array, it works one way. If you're using only local disks in your local server without any RAID controllers, it works a little differently. So there is, basically all I'm saying is that I want to show you how the performance numbers differ, but whether this is the right thing and safe thing to do in your configuration with your database version, that's you have to do this research yourself. Okay, but it exists for a reason. So let's do a restart. Stop MySQLD, and well, my Postgres benchmark is currently stopped. So, and let me just do a start again. Okay, so now we should be doing less of this fsync calls. And see, what was the top call? Fsync, right? Which ended up having to flush. I mean, it ended up having to wait until the XFS kernel worker threads had flashed and synced the journal metadata to disk, right, before continuing. So that's what they were doing. So let me run the benchmark again. It has like 160 million rows across 16 tables. See, and you see it already is. Let me maybe the first one is a bit an outlier. You see it's like 4 times faster, right? And you see one of the reasons why I wrote this tool is that when you run benchmarks like that and something is like 4 times faster than the other option, then well, you don't want to just say, hey, I guess it's always faster. I mean, you can actually measure what's going on, right? So in my case, let's run the psnapper again, and let me I'm gonna run it without the k-stack first, just to have less information here. So we get 4 times more work done, or even maybe over 4 times more work done, and you see the top kind of a state now where time is spent is actually, that's a good thing. We're reading something from disk, we managed to submit the IO, and we are sleeping waiting for the IO to complete, right? So, and there is some fsync here again. I don't know what's where it comes from. We could probably do some MySQL stack sampling for that, but we get over 4 times more work done, and also you see, and the reason why we get more done is that we don't have to wait for fsync so much anymore, right? So I'm not even going to show the stack trace again. This is a fairly quick overview. All right, and I'll run. I'm not going to demo this more. Just a quick overview. I'll run a Postgres benchmark. So if I can run PSN, let's only look into any process or thread which has post in it. There is something cool that Postgres does. You see, it shows like it's a postmaster process, right? And but again, I want to choose my own columns. I'm gonna say with small g, I'm gonna choose my own list. With capital G, you would just add to the end of the list. I'm gonna say command line. So this is another place in proc file system for every single thread, right? And state. Let's use syscall as well. So now we are sampling Postgres processes. Okay, and you see, I forgot to use sudo. I'm using syscall, and I forgot to use sudo. It tells you, hey, I tried to sample these proc files, but I couldn't access any of them. So run as root or avoid restricted files like syscall, or measure your own process only, and so on. So all right, and here we go. So what this right side is the same story. Like MySQL, you see what kind of system calls it's using and so on. But the cool thing is, you see, Postgres actually names its threads, right? So you can actually examine from the OS. You don't have to list the task, to get the thread ID and query it from the MySQL. You can actually use the command line because Postgres has been instrumented. So it's actually pretty cool. You could do it for MySQL as well. So I haven't contributed to MySQL, but you could name every single MySQL thread as well, right? So you'll see like, hey, we have a bunch of idle sessions, I guess, or idle in transaction and commits and so on. Okay, or you can even remove the state if you don't care about the state and syscall. I mean, just run it like that. So this shows you all Postgres sessions which are either running or disk, but doesn't show you the sleeping ones, right? Or which are in the like sleeping as far as the OS can tell, right? Okay. And yes, so this is even though Postgres is like a multi-process engine, then you can do this thing on Java even, and multi-threaded things as well. You see, it's actually a pretty new blog entry of mine. You see, I'm using the same trick that I already showed. You run PS on the Java, program, and do the group by and top 10, limit top 10, and so on. And you see, Java names its threads as well, right? And you even see the garbage collection threads. And in my case, I used the benchmark tool for Oracle data generation, and the developer has named threads as well. These threads for generating addresses, and you see there's a bit of garbage collection activity as well. Okay, so that's pretty cool. So this hopefully helps. I have a couple of additional slides here. I'll upload the slides to SlideShare as well. Here is an example of running a psnapper on just a specific PID, and you see it's a dd command, and it looks like it's bottlenecked on the target side. You see, 79% of time we were waiting for a system call right against this file, right? I forgot to show the file name thing. You see, you can run psn-p mysql, and I think you gotta be sudo for that. And let's also add file name, right? So those system calls that only take one argument, or one file as an argument, I can show. Some system calls like async IO submit, I cannot show that file name because I cannot extract it from the proc file system. But you see, it shows you even like against which file we tried to do the IO. And I have the latest version of psnapper has like a file name sum here as well. And you really probably want to know this in the context. Let's put the syscall here as well, because you really want to know whether you're reading or writing, right? So the sum just replaces any digits with a star, so you will get a better summary. You see, apparently the heaviest files, what our threads are spending time on, is this guy. You see, fsyncing is still used, but on the log file, bin log, and this is from this is a fairly recent improvement in MySQL, right? So you have this double buffer writer or double block writer, whatever it was called. So you wouldn't have to do all this I/O against a single system table space and end up waiting for this semaphore contention and so on. So they are improving scalability here. Okay. All right. So all right. And the last thing to show is it's the same thing but over time. So if you go to the Xerox Tools, I have a whole video and a lot of it's a long document, right? And before that, let me just run it. You see. So this is a tool which is designed to capture every second. It runs every second and captures by default the threads which are in R or D state, right? And you will write this into an output file. I mean, right now this by default, I just run xcapture, it will show it this on the screen. But if you say output dot, so now this will create an hourly file. For every hour, it creates a new file with a new name, and you will have a full history, right? Okay, so you see it created an hourly file, and it's like a pure CSV. So and you can go wild with it, right? You can do whatever you want. I mean, put it into a database or run DBA style or another sysadmin SQL against it, or use it whatever way you want. You can feed it to Grafana or whatever. So I think the high system load, right? So if you have high system load on Linux and you have this xcapture enabled, you see, you can come into the office next morning when you need to go back in time and troubleshoot this thing, and you just do it. It's again DB, it's a sysadmin SQL, select everything from this file where timestamp is this, right? And by the way, only take this, these columns, select only these columns, and then do a group by, by all these columns. And by the way, show me the top 20 or whatever lines there are, right? And even I'm actually taking a whole minute here. I'm zooming into 1 minute. I had a spike during some minute, and I didn't have 30,000 threads in this mode. I should probably divide this by 60 because I'm sampling every second, right? And I'm looking into a whole minute. I should probably I should divide this by 60 to get how many threads I had, on average, in this mode, every second, right? So you can read more about that, and if you look into my blog about this, or if you go to Xerox Tools, then you even see there is a tool called Visidata, not written by me, but a tool called Visidata, and you will see what it does. See, it's like a pretty cool text file analysis tool which allows you to do group bys and whatever, and even briefly show you like histograms, which kind of a state took the most time, and so on. So that's the tool is called Visidata. So that's pretty cool, right? And talking about tools, so there is this is not a public tool, well, yet anyway. It's kind of in a stealth mode, not by me, but built by a friend. And here is an example of Xerox Tools. This X capture data, it's already visualized, right? And you'll see it's running Oracle, and it's running Postgres on the same machine. It's running Java, and you'll see from OS level, you will get a breakdown of what's going on, who is using, who is spending time in your OS, and you can even zoom into specific processes, or what were the top system calls. You see some sort of a spike here. Let's say this is a spike of some sort. What was it? What kind of system calls were the top, or what were the top number of threads in different system calls? So we apparently were writing, and I think there is a Postgres version as well, that you have a Postgres. This data comes from inside Postgres. Some of you may recognize these events, but if you go down, there is the similar sampling is done from at the OS level as well, and you see these are the Postgres names, and you'll even see that there was a thread which was using CPU mostly, and you see what system calls they were on, and so on, right? So what I'm basically showing you here is that sampling thread states, going beyond just whether we are on CPU or not, looking into system calls, wait channels, and even the kernel stacks, right? That will it will help you a lot. And I did not have to install any kernel modules, enable traces, upgrade, nothing. This works in Red Hat 5 as well, this approach. You won't have as many columns, but starting from Red Hat 6 clones and so on, it's gonna be pretty powerful. And in some cases, you don't even need to use, you don't even need root access, right? So, this X capture you just saw, while the P snapper is written in Python, I wrote X capture in C, because for efficiency reasons, and it's like 400 lines with all the comments and so on, and it doesn't have any dependencies or agents or anything else you have to install. It just uses the standard Linux, libc features that are already there. Okay, and it's open source. You can extract it any way you want. I didn't have time for this, but there's not much to say about the CPU, or there is not much of an invention. But when you run perf, you can actually schedule perf to run and sample at 1 Hertz and keep it running forever. And I think you will see from here. You see this run X CPU, what it really does, it runs perf. It says sample once per second, right? And by the way, every minute switch output to a new file. So you'll have a bunch of files in here, right? You might want to compress them and so on, but but I've done things where I have to go back to the previous, weekend or whenever a spike or some sort of a CPU hiccup happened, and say, okay, let's run perf report on this file that was created on that particular timestamp. So I'm zooming into just 1 minute of time, and indeed I can already see what's going on, right? Or where to look next. So no need to guess. So my psnapper and xcapture, they measure thread states, and they are useful for sleeping, when you're stuck and sleeping as well. But perf in this mode only samples when you are on CPU, right? So there are these two worlds, and both are covered by different tools. Okay. All right, and that's it. So I have plenty of blog entries about Linux, a lot of Oracle stuff. I have long hacking session videos about these same things. Xerox Tools live here now. You can follow me on Twitter, send emails with questions, or in the Slack channel as well. And by the way, I have upcoming events as well. I do online training not only for Oracle troubleshooting but also Linux troubleshooting as well. Okay, thank you very much, and let's get into questions.
Thank you so much, Tanel, for taking time, joining this call, speaking for MinervaDB Athena 2020. Welcome to MinervaDB Athena 2020. Great to talk to you, man.
Thanks very much. Great to be there.
Thank you. Actually, your topic is the only talk for the entire event of 12 speakers, and on the Linux performance. We have speakers who talk about database systems performance on MySQL, MariaDB, and PostgreSQL. And the performance interpretation are more on using the native performance forensics tools provided by respective databases. They work great. Now, when I go through your talk, when I hear your talk, it's like how you interpret the story is bottom up than top down. Top down for me is like, hey, my database is not doing good. I look at like what are the data dictionary views I can use to interpret it, or what is a slow query log. Take that out as raw, and then annotate what I wanted to annotate and build it. But you are looking at from the hardware to the Linux and then the Linux probes, which talks to several database services. Can you give us some insight about how this viewpoint will impact and influence a performance engineer?
Yeah. So it's good that you mentioned the bottom-up approach. So I will start by saying that also in my mind, the systematic approach should start from the top. You start from the user who complains or the application that runs slowly, and then you drill down deeper into the database level, right? But not all problems originate from the database level, right? You have a very high I/O throughput system. You may have all kinds of problems happen there. And as you mentioned, sometimes you cannot even log into the database because it's so slow. So, but you can still access the server. So what do you do there? So my talk will be about this bottom part of the full story, right? So ideally, you still start from the top, but at some point you may want to look into the OS level. And the insight before to talk about the tools and data sources is every application, including MySQL, Postgres, Oracle, they're just applications, written in different languages, right? Some are more complex than others. Every application is a bunch of processes or threads who will try to, who will sometimes sleep, sometimes voluntarily go to sleep when they wait for a lock, sometimes involuntarily go to sleep when OS puts them to sleep because of the synchronous I/O and so on. So, so basically, every application and database engine is a bunch of threads who will try to do some work and then go to sleep for various reasons. So, and at Linux level, you can measure these thread states, using the proper file system. So you don't even need ttrace or BPF or anything like that. So the concept I call it thread state sampling, or on Linux they call threads tasks, task state sampling, right? So I have written a tool, open source, where you can sample what every thread does in the operating system at low frequency. I usually do it at 1 hertz, once per second, right? And then you have this output log, right? And when you have a problem, that happened yesterday at 3 a.m. and you finally get into the office by the morning, you can look into the historical files of what were all these threads doing. And it's not the full trace, because that would fill up your disk, but it's just a low frequency sampling of thread activity from past, right? And the difference will be this, that somebody is late in coming into the office and they say, I was late because the traffic was slow, right? But what does it mean? But the thread or task state sampling allows you to drill down into that. Okay, how many lanes you had on the road, on the highway? How many lanes were full of cars? How long the cars were? What color they were? You know, who were driving and so on. So you will actually see, you're not going to see the full picture of every car that filled the road, and that's why you were late. But you will rather see a statistical summary of what were the slowest moving cars, what were the longest cars, and then, you know, how many lanes you would actually need, right? So to, you know, get into the office fast enough. So instead of measuring utilization summaries, like, hey, what was my CPU utilization, or what was the average IO time? You know, these are secondary metrics, but the primary metric is like, what were my threads doing, right? So that's the starting point. So the tools that I'm going to show you will make it easy to sample and report what every single thread does in the operating system. And it's a little bit microscopic in the sense that you know, you will see the thread states as the operating system sees it. Like, were you on CPU? Were you doing disk IO against this file or that file? Or were you waiting for a kernel spin lock because you have some kernel problem, right? It shows you all of that. But but you know, there's a missing piece here. But what if I see that everybody were trying to be on CPU for 99% of the time? You know, there was no IO problem, right? Everybody was trying to be on the CPU. So, well, let's sample CPU activity too. And you need a separate tool for that. I mean, again, I'm not doing eBPF yet because I want to support all old Linux versions as well. The second tool you can run is just perf. You know, very widely used tool on Linux. And but few people know that you can run perf and make it sample, keep it always on, and make it sample whoever is on CPU at 1 Hertz frequency. Again, low frequency profiling of production systems. That's always on, right? So you can see both problems that arise from IO or OS kernel issues, or, you know, whatever makes your processes sleep. And the second part, running perf at 1 Hertz frequency, will actually give you a statistical sample of anything that ever happened on CPU, right? And it's all so low because we're not doing high frequency sampling. It's so low overhead that you can keep it on 24/7, right? And that's the story.
Wonderful. This gives a new way of looking at the performance metrics. I tell you why. If you look at from a performance troubleshooting, right? We always many times we always try to end up detecting or doing forensics of symptoms, not the actual problems. Like when I'm looking at a provided data dictionary views, which says that there are 10 top files of tables and indexes. These are the files which causes extensive disk IO. So that shows that the blame goes to do I need a faster disk, or have I done a wrong capacity planning or sizing? And that lead me to solution of the problem, but then the cost of solution is going to be high because it's going to be an extra investment. Now, when I follow yours, right, where you are getting into the macro level details, like, hey, what is going to be the relative thread performance of, say, 100 threads concurrently run on a time series pattern, right? Which are the threads which are being really needed, and which are the ones which are the rogue threads actually. So this gives us to solve the problem, not solve the symptoms actually.
Exactly, because the primary metric for performance is time, you know, period, right? Users don't care about anything other than time, right? You know, your CFO may care about how many CPUs you rent from Amazon and so on, but essentially it's all about time. And then when you focus on time, and when you measure time, like I mentioned, you can break down the time. Now, you can summarize or slice and dice it from many different angles, right? So it's like, okay, show me which users and which SQL statements were doing the most I/O against this file that's in some slow storage or something like that. You can do slicing and dicing like that. So you'll just use different ways to break down time, and then drill down deeper into secondary metrics like utilization or I/O latency or how busy this disk is. You will drill down where needed, but the starting point is time, and you will find where whatever the initial time breakdown points you towards. I mean, are we waiting in kernel for some spin lock, or are we just doing I/O? You'll just follow the path there, and that's what I call a systematic approach. But you can only do it if your tools support it, because again, 20 years ago, you didn't really. Well, Linux proc file system was there, but it didn't have everything you wanted in there. Perf was not available. You had something called O profile. I'm sure you've used that.
Yes.
But it was like,
Yes.
it was not easy. Sometimes you hung your server and so on. And that's when you ended up doing metric voodoo. I call it metric voodoo. You run SAR, and you see that the ratio of this to that is like, a little bigger than yesterday. And that's when you end up doing metric voodoo, and you try to reason about what the root cause is based on secondary metrics, right? But you should focus on time. Then you don't have to do metric voodoo, except in very extreme.
Exactly. If you, as you rightly said, if you look at the visibility to the performance metrics were thin 10 years back. Today, I have access to quite a lot of information. This also leads to
everything.
this also leads to a new concern for me. Like me as a performance engineer for database systems performance, I also heavily depend on the logs generated by the database system. Like when I'm troubleshooting MySQL, I heavily look at on something called MySQL slow query log. This is all about all the slow queries logged in, which are expensive from a response time than X seconds. It could be even 0 seconds. Now, today, if you look at, I just have that, and it's good enough for me to understand, at least from a cockpit view perspective, like, hey, this is where the bottleneck is. Today, the whole story is changed. Today, I use several tracing tools. Like I use eBPF, I use dtrace, I use several Linux probes, like what you are building. This also lead to the point that I'll have tons of log data to interpret. What do you think is like the possibility or probability of me getting lost on the evidence? Getting me right? I mean, now overwhelmed with the amount of metrics I have to interpret. So in such equations, what do you tell, like, the 5 metrics, hey, this is the 5 metrics you need to look at. More you collect is good. But if the 5 metrics you annotate, you interpret can influence the performance by, say, 80%, then I would say, like, those are something which is really the need of the hour for you. Like, finish these 5 metrics first, then you get deep into it for your interest. So you got my question, right?
You gotta focus on some fundamental metrics, ideally break down the time where time is going anywhere in your stack, right? But I would exactly say that, it's a slippery slope. You have a performance problems, and you cannot always solve them, and then you just do some Googling, and somebody says, hey, you gotta install Prometheus, right? And you gotta now collect and put these 500 different metrics into Grafana, and then you see a big dashboard with 500 different metrics. It's okay, what should I do? Should I go through all of them and see if there's anything if a number is bigger than 70, then it's bad, right? Or if the ratio to this or that is off, then it's bad. And then people are like, hey, I cannot deal with it. Let's have another project. Let's do machine learning and anomaly detection on all these secondary metrics. And now you get 1,000 alerts, warnings per minute, because some metrics seem to be off. So that's the metric voodoo. That's a slippery slope. It's so easy to collect more metrics nowadays in hope that, hey, maybe this will be the big breakthrough, but actually no. So you don't want to do metric voodoo. You just have to focus and systematically drill down, into what matters, and that's time, right? And then whatever these time breakdowns show you, that's where you will go deeper with other tools. And luckily now there are options available. I mean, I would still, again, when an application server experiences query latency, I would still not go to OS level as a first thing. I would still look into either query log or app server logs, or whatever app dynamics, or whatever the end-to-end latency instrumentation you may have, right? But there will be a point in some cases where explaining your query problems by optimizer issues or whatever, that's not enough. You see, every commit takes, I don't know, 70 milliseconds instead of 1 millisecond, right? So why is that, right? So and that's where my tools come in, right? So they will bridge the gap between your database threads and secondary metrics tools like, I don't know, IOStat, whatever. So before you go into these low levels, you want to know what's going on in between.
Right. Like by now you shared with us that what is the best way to do a performance audit of your infrastructure. Now, what do you think can be a mistake, like from a performance engineer? What do you think is like should not be the way you should look at a performance metrics and troubleshoot?
Yeah.
You said in between that don't Google and interpret, because Google may not be always right. I share with you one personal experience I had. One of my during my consulting engagements, one of my customer like, hey, we are finding Linux continuously swapping out MySQL. We just went ahead and disabled swap. It was great, but then at one fine day, it is like the entire system just froze. In the sense, like the system, the Linux, presumed that there is infinite memory is there when they disable swapping, right? So from your experience, what do you think is not the way to do it? Like if you're a performance engineer, don't do these three things. That will really you're shooting your feet.
Yeah, so I would say that it also depends on what is the background of the person trying to solve the problem. So as typically a developer, when they see that the database responds slowly to a query, and they just conclude that, hey, the database is slow. I guess MySQL cannot scale, and therefore, I need to start building caches in apps and so on. So when something is slow, don't just assume that this is inherently always going to be slow. So don't assume that this problem is unsolvable before drilling down into it, right? So and that's when the application person should either look into database metrics or the query log or execution plans, whatever. Again, depending on whatever query takes the longest in your critical path, right? So drill down. Don't just give up and say that databases are slow, right? And the other end is often people who come from sysadmin backgrounds, right? They a user complains something is slow, or the app server complains, then the sysadmin type logs into the Linux box, runs SAR or runs top, and says, hey, the CPU utilization is only 20%, therefore you don't have a problem. Or a similar version from the MyDBA days is Oracle was slow. We followed that most of the time was spent on I/O, disk I/O, and then you go deeper, you run IOStat and see that the average latency for I/O is like 1 second instead of like 10 milliseconds back then. And you went to the storage guy, and storage guy came back like in 2 hours and said, we did a health check in the storage array, the bottommost layer. The health check said that all the queue lengths were okay, therefore you don't have a problem, right? So I think the two ends are, one is like when you do drill down analysis, you have to do that, but don't give up. If the database is slow, talk to a database guy, right? And if the database points to the OS level, talk to install my tool, right? Talk to the OS guy, right? And the other option is the other issue or the problem is that especially if you're a sysadmin or storage admin, you cannot assume that the top layer doesn't have a problem if the bottom layer of yours works well, because maybe the pipe between the database and the storage, maybe there's a problem there, right? You cannot just say, hey, I don't see anything, therefore you don't have a problem, right? So hopefully it's not really a list, but it's a range of behaviors that you shouldn't do.
Completely understood.
You finish that up. I mean, that's exactly so how you should do things is exactly this. You start from top, and wherever the evidence leads you, is it a slow query log, or is it some sort of other, you can do thread sampling inside MySQL and Postgres as well. You just query sys processes, or whatever the view was. You query it every second, store the output into a table, right? And when a problem happened at 3 a.m., you actually have an idea of what cars you had on these roads, right? So you follow them. You just layer to layer. How I call it is, there's I don't know if it's the right word, but children's game, treasure hunt, right?
Yes.
Treasure hunt. I played when I was a kid. You don't know where the final treasure or artifact is. You only can know where the first one is, and the first one will point you where the next one is, and the next one will point you where the next one is. That's how you drill down through layers as deep as you need to go. So you cannot. So I guess this is the third thing that you shouldn't do. When you have a problem, don't ask me how do you. My query is slow. What parameter should I change? That's you're trying to skip a lot of steps. And if you start flipping parameters right away, you're going to be not systematic. I mean, you're going to be dependent on luck, right? But you don't want to be dependent on luck. So you start from the top, you measure your slowest queries, and maybe use my tool if it's feasible later on to see what were these threads doing at OS level. And maybe this will point you to a optimizer problem. Maybe it points you to a storage problem, whatever. But you're not going to just try to go and change or reboot everything, whatever. Just maybe it helps, right? Be systematic.
Right. So if I conclude the recommendations what you shared now in this conversation, if you are collecting the performance forensics data, they are definitely not the true story. They're just the interpretation of the true story. Now, if you want to derive meaning from that, it's better go deeper until you find the metrics which is connecting the whole story.
Yeah, connecting, right? Exactly.
Got it. So that's all on the discussion on this virtual fireside chat with you, Tanel. It's been a privilege for me to talk to someone who has spent more than 2 decades in performance engineering. Has run a lot of blogs. Is a very much sought after speaker for a lot of performance engineering conversations and conferences. Thank you so much, Tanel, from MinervaDB Athena team, MinervaDB, and the entire attendees of this conference. It's a great pleasure to have you in this conference, Tanel. Looking forward to having you in the future conferences also.
Yeah, I mean, what you're doing is cool, and thanks for inviting me. And see you soon at the conference.
Wishing you a Merry Christmas in advance, a great 2021, where the world is again free. All of us can travel, meet again people.
Yeah.
Get
let's
out
do
of
let's do 2020 again, right? So, but this is gonna be the real version 2.
I look forward to that. Seriously, I wish that too. Thank you so much, Tanel.
Okay, thank you.
Yeah.